Okay, in this lesson, we are going to describe about energy in simple harmonic motion. Let us turn back to the mass spring system. Um, we recall back the equation for the displacement of the mass, which is described by the displacement as a function of time is a cos omega t. And then the velocity of this mass can be described by this minus omega a sine omega t. So since this mass is oscillating, that means it has a velocity. So when it has a velocity, it brings kinetic energy. So the kinetic energy we call back as a k equal to half mv squared, and this v always changes with time. And if we investigate in detail, at this point, the velocity of the mass is zero, so the kinetic energy should be zero, and it become maximum here, and again zero. So other than the kinetic energy, because this is a spring, this spring can have can store an energy in the form of elastic potential energy, which is E is equal to half kx squared. K is the spring constant, x is displacement. So if the spring is compressed or stretched, it will gain elastic potential energy. Alright, so let us consider what happened to this both kinetic and elastic potential energy at three important displacement. First, for when the mass is at the equilibrium point, so that means the x is zero, so we will have the zero elastic potential energy. And then when we stretch it, we have half ka because now x equal to a, so we have a maximum is half ka squared, the maximum potential energy is half ka, and when the mass is at this point is negative a, substitute to the x here, minus a, so because we squared this minus a, we get the same value, so the potential energy is maximum at this point and at this point. For the kinetic energy is zero here because the velocity is zero at this point, so zero kinetic energy and maximum kinetic energy at this point. Alright, if we consider this mass spring system as an isolated system, its total mechanical energy must be conserved. That means the total mechanical energy is equal to kinetic plus the elastic potential energy, and this value should be constant. Okay, constant. So you see, if, from this kinetic energy and potential energy, the kinetic energy depends on the velocity, and the potential energy depends on the displacement. Alright, so since these two types of energy change from zero to maximum and zero, and for potential energy from maximum, zero, and maximum, so there is an exchange of energy between kinetic and potential energy. So this the sum up of them should be constant, but this value at certain moments all kinetic energy, all mechanical energy become elastic. At this moment, all mechanical energy become kinetic energy, right? So we can have this relation where the total mechanical energy is equal to k plus u, which is also equal to the summation of these two types of energy, and also equal to the maximum potential energy and equal to the maximum kinetic energy. Alright, so from here, from this relation, from the previous lesson, this relation can show us what happened to the velocity along at any time. By using this energy relation, we can also deduce another relation between what we call it as a velocity at any position. So we can find out, even though we know the velocity is zero here and maximum here, but what is the velocity at any other position? So to find out that, we can have this maximum potential energy and this summation of the energies. We put it out here, and you find out that this half can be cut out. Okay, and then rearrange back here. Put this kx over there, and factorize this k. Bring this m downwards, and then make a square of it. So we have plus minus because we get this square root of x squared minus x squared. So from the previous lesson, this k over m is equal to omega. So that's why we can simplify this relation so that the velocity as a function of time of position is given by this relation. All right. So now let us investigate the graph of the energy versus time. So what happened to the energy versus time, and also the energy versus position. Okay, based on the this displacement over time. So this is the profile of displacement over time, and this is one complete cycle. Okay, so let's look first to the potential energy. So for potential energy, is a U equal to Kx. So you see here, at this point and at this point, the potential energy become maximum. So it should be here. And then at this point, the potential energy should be 0. So this 0. And then at this moment, again, the potential energy become maximum. So you see there is a change of the value of potential energy from maximum, 0, and maximum again. And then continue to this point. So at this point it is again 0, and then complete one cycle. This is a maximum potential energy. So you see that there is a change of energy from this point to this point, and this corresponds to one complete cycle of the oscillation. Alright, so it is equal to half kx squared, and half x is this relation, and if you square it, you have x squared cos, I forgot here, this is cos square. Alright, so you see that the energy will not become 0 in this part. It's always positive because of this cos square omega t. For the kinetic energy, in a similar way, let's consider at this point. So at this point, the kinetic energy should be 0 because velocity is 0, and then get maximum at this point, and minimum again, which is 0. Continue here as a maximum and maximum velocity, and then here is the 0 velocity. So you have 0. So this k equal to half mv squared, where this v is here, and you square it, you have a this is sine square. So again, you have a sine square, which is it will never be 0. And then if you sum up this green and this red value, you will have a constant total mechanical energy. This is for energy versus time. For the energy versus position. Okay, energy versus position. So you have only two extremes at minus a and a. So let's look at the potential energy first. So this is potential energy. So at this point, the potential energy should be maximum, and then get 0, and then maximum again, and then return back. So the graph is just circulating around this area. For the kinetic energy, at this point it is 0, and then get maximum, 0, maximum, and so on. So you see this graph is a quadratic because we have x squared, and the addition of the green and orange will have a constant total mechanical energy.